Hi, our project is implementation of DWT for image compression using EHRCA for HD videos, biomedical and smart antenna applications. The aim is to design an effective two-dimensional discrete wavelet transformation based image compression technique. In order to achieve best performance, EHRCA has been designed using Verilog hardware description language. Here two types of compression known as the row compression and column wise compression is done. In proposed DWT models, adders are recognized as high potential than other components. In order to improve the efficiency of DWT process, an efficient adder called enhanced half ripple carry adder has been designed in this work. Proposed EHRCA circuit offers 10.71% improvement in hardware and 11.78% improvement in total power consumption than the traditional binary to XS1 conversion based square root carry select adder. Further, proposed adder has been incorporated into row wise compression and column wise compression for improving the architecture performance of DWT. Three levels of decomposition are made for image compression. With the help of pixel values of image and EHRCA adder circuit, 2D DWT image compression technique is implemented to the Verilog HCL design. The performance of EHRCA circuit is better than the conventional binary to XS1 based square root carry select adder in terms of silicon area and power consumption. Hence, the performance of DWT is also increased when incorporating EHRCA circuit into addition process of DWT computation. The adders of the digital circuit and wavelet transformation play a vital role. The project is developed with the help of adders in order to develop the enhanced half ripple carry adder. The wavelet transformation is used in order to perform the compression. A wavelet is a mathematical function used to divide a given function or continuous time signal into different scale components. The Haar transform is the simplest of the wavelet transform. This transform cross multiplies a function against a Haar wavelet with various shapes and structures. Like the Fourier transform, cross multiplies a function against a sine wave with two faces and many stretches. This formulation is based on the use of recurrence relations to generate progressively finite discrete samplings of an implicit mother wavelet function. Each resolution is twice that of the previous scale. Discrete wavelet transform is the image compression technique in which low pass filter and high pass filter is involved to compress the image as level by level. This is the block diagram of 1D DWT. The original data is fed into high pass filter and low pass filter, which is downsampled by 2 in order to obtain the average and detailed coefficients of DWT. This is the basic block diagram of 1D DWT. The block diagram differs from the type of dimensions. The 2D DWT technique has multi-resolutional decomposition capability because it plays a vital role. Block diagram of 2D DWT. The original data is fed into high pass filter and low pass filter. Both are downsampled by a factor of 2. Again, the sampled output is fed into high pass filter and low pass filter, both in uppercase and lowercase respectively, and all those signals are again downsampled by 2 in order to obtain the HH, HL, LH and LL coefficients. The structure of DWT level is very important in order to determine the level of HH, HL, LH and LL coefficients. This is the structure of DWT levels. An input image is passed through a series of filters to calculate the DWT coefficients. Literature survey. A survey has been done through which the project is developed. A lot of papers has been referred with help of our internal guide, and a series of information has been gathered in order to confine to a particular object which contains information about our project. Nearly 10 to 15 papers have been surveyed and a crisp information from each and every paper has been obtained. The proposed system is the usage of EHRCA in DWT compression. The ripple carry adder is relatively so since each full adder must have to wait for the carry bit to be calculated from the previous full adder. The gate delay can easily be calculated by the inspection of full adder circuit. Each full adder circuit requires 3 levels of logic. In 32-bit ripple carry adder, there are 32 full adders so that the critical path is nearly 65 gate delays. A design with alternating carry polarities and optimized and or invert gates can be about twice as fast. RCA is one of the basic adders to perform the binary addition process. However, CPD is the main disadvantage in RCA circuit. In order to reduce the problem of CPD in RCA circuit, enhanced half-ripple carry adder is developed. The circuit diagram of enhanced half-ripple carry adder circuit for 4-bit is illustrated in figure. It consists of half adders, OR gates, AND gates and multiplexers for performing addition process. As the name itself, final half of the circuit only must have to wait until carry signal load from the previous stage. Remaining circuits can execute in a parallel manner. Therefore, the EHRCA circuit seems to be well efficient and it provides a greater performance when it is compared with the ripple carry adder circuits. Hence, this adder circuit is named as enhanced half-ripple carry adder. On the other hand, the structure of this circuit is that SQRT CSLA. Instead of RCA BEC combination for carry input 0 and carry input 1 respectively as CSCA circuit, simplified circuit is designed as shown in the figure. The carry input is considered only for final stage of EHRCA, whereas remaining circuit can perform the respective computation in a parallel manner with the help of available input data. Similar to figure, the EHRCA for 8-bit and 16-bit can be developed. Further, the EHRCA adder is incorporated into the addition process in order to increase the performance of 2D DWT. Three levels of decomposition are made for image compression. The performance of conventional SQRT CSLA and developed EHRCA circuits are analyzed in results and discussion. The EHRCA provides a better performance both in terms of silicon area and power consumption. The realized output values from the EHRCA circuits provides less delay in time than the conventional circuit. A tabulation has been provided in the results in order to show the better performance of EHRCA when compared with the conventional BEC circuit. The block diagram of EHRCA circuit is now shown here. It consists of, for a 4-bit EHRCA circuit, it consists of 4 half adders, 4 muxs and 1 carry input and 1 carry output. The simulation is calibrated by using both Xilinx and Matlab. The Xilinx is an interface with the user in order to design for digital circuit in an easy manner. The output can be realized in an easy way with less complexity and synthesis report can also be obtained. The Matlab is a multi-paradigm numerical computing environment and 4th generation programming language. The typical uses include math and computation, algorithm development. Many types of language can also be used as an interface such as C, C++, Java, Fortran and Python. modeling, simulation, prototyping, data analysis, exploration, visualization, scientific and engineering graphics, application development, including graphical user interface buildings, are some of the typical uses. The Xilinx and Matlab provide a variety of outputs when it comes for the EHRCA circuit. Many types, three levels of compression are made using Xilinx, and three types of compressions are made using Matlab. The input image consisting of the pixels is fed as an input image using the Matlab. The Xilinx is used in order to produce the digital outputs. Results. Enhanced half ripple carry adder is designed using Verilog hardware description language. Here the output is obtained using Xilinx and Matlab. The RCA circuit is realized and identified the redundant logic operations. The performance of conventional BEC based SQRT, CSLE and developed EHRCA circuit for 16-bit is compared. The image of multi-resolution decomposition capability. Three levels of decomposition are done to compress the image with the help of EHRCA. In reconstruction, input data can be achieved in multiple resolutions by decomposing the LL coefficient further for different levels. The compressed data is upsampled by a factor of 2 in order to reconstruct the original input data while performing interpolation process. The EHRCA circuits requires less delay, and the carry input is only required for the last part of the circuit which is designed. The EHRCA circuit provides less complexity, and the cost of designing the circuit is very low when compared with the other circuit, but more number of components is required when it comes in comparison with RCA. This is the input image. The input image is obtained by combining the pixels in Matlab. The pixels are converted into the input image. Three levels of compression is obtained using Matlab. The image can be compressed into row-wise compression and column-wise compression. The row-wise compression output is established over here. In row-wise compression, three levels of compression is obtained. The image is compressed in such a manner that the rows can be used to identify them. This is the level 1 compression. This is the output for DWT level 2 compression. This is the DWT level 3 compression in Matlab, and this is the final stage of compression in Matlab. This is the overall DWT compression outputs in Matlab. The first figure indicates the input image, second image indicates the row-wise compression is carried out, the third image indicates the level 1 row-wise compression, the fourth image indicates the level 2 row-wise compression, the fifth image represents the level 3 and the final level of compression using Matlab, which is obtained for the input image, which is shown here. The Matlab output is very important in order to show that the pixels are converted into image. Only when the pixels are converted into image, there will be a clear visualization in understanding the fact that images are composed of pixels. So, compressing the image can reduce the memory allocated for the image. Therefore, the size of the image can be reduced. Reducing the size of the image is generally called as image compression. The size of the image is very much compressed here using the row-wise compression. The row-wise compression provides better ability for the processes to be carried out by the processes, so that the size of the image, which is now well reduced, can be processed soon. The image compression can also be obtained in digital manner. In order to obtain the digital outputs, the Xilinx software is used. Three types of compression is also obtained in Xilinx, such as DWT level 1 compression, DWT level 2 compression and DWT level 3 compressions respectively. This is the DWT level 1 compression in Xilinx. The compression which is obtained in Xilinx will be exactly equal to the compression obtained in Matlab. This is the level 2 compression which is obtained using Xilinx. The level 1 compression and level 2 compression is well differentiated. This is the level 3, which is the final level of compression using Xilinx. This is up to the output of the EHRCA circuit. From the table it is clear that the EHRCA circuit offers 10.71% reduction in silicon area and 11.78% reduction in total power consumption than conventional BEC based SQRT CSLA circuit. The developed circuit consumes less hardware resources and power consumption than conventional BEC based SQRT CSLA. The reduction in power and silicon area consumption than conventional BEC SQRT CSLA circuit is more. Further, developed EHRCA circuit is incorporated into additional process of 2D DWT for image compression. 3 levels of decomposition are made. Simulation results for image compression using 2D DWT is validated by both Model Sim 6.3c and Matlab simulation tools. This is the comparison table for 16-bit conventional BEC based SQRT CSLA and developed 16-bit EHRCA circuits. It is clear that the delay, slices and LUT and power in megawatts is shown clearly here. From this table it is clear that 16-bit developed EHRCA circuit provides better performance than the conventional BEC based SQRT CSLA circuits. In future, the developed EHRCA based 2D DWT will be helpful for image processing like compression, segmentation and fragmentation. It is also be very useful when the input data to be fed is compressed so that the memory can be reduced in HD video, biomedical and smart antenna communication systems. Thank you.